Okay, it seems it's recording. So let us start our discussion. Yeah, now tell me which problem you wanted me to discuss. So this is in SAP. I think regarding the lateral tie, someone asked me. So I'll be discussing that one. Okay. So here you can see confinement material. This is regarding the lateral ties. Okay, or stirrups in case of beam. And this is the material you can specify for the stirrups if you have the grading of the steel different than the main steel. Okay, so from this drop down menu you can select. Then here you can decide the bar diameter for the lateral ties or stirrups. And in the last discussion I told you the D means for Indian standard. Okay, so you have to go for D if you design or analyze according to our Indian standard. So let us consider 10 mm diameter lateral ties or stirrups, and here you can specify the longitudinal spacing between the stirrups or ties. Okay, let me keep it as 150 mm, and number of legs, for example I want to give 4 legs, and 4 legs in both the direction. Okay, then you just have to click this. That's all, and this is regarding the main reinforcement. Okay, HYSD or whatever grade you want to decide, again you can select from here, and this much only you have to do. Okay, now tell me what doubt you had in this. Let me know if you have any doubt in this. Anyone?
Excuse me, sir.
Yes.
Sir, how can we change the value of epsilon SU in the concrete model that you had recently opened?
Okay, let me go back to that again. You are asking about where was that? This one.
Sir, last
Sorry,
value
this is
epsilon
epsilon.
in
This
SU.
one, 0.12.
This one. Yes, sir.
Yeah, this.
Yes, sir.
1 minute. Actually, I also didn't check this one. Let me try. Yeah, so you can actually you have to first edit the material definition. So as you have seen, I have changed that epsilon SU there from 0.12 to 0.14 and automatically it considered here. Okay, it means whatever steel you are considering, so epsilon SU defined under that will be considered here. Thank you, Nagliji.
Okay, sir. Thank you.
Okay, so I think it's clear, right?
Yes, sir. Thank you.
Okay. Okay. So any more doubt? Anyone else?
Sir, while modeling this flange section uh, that was given in the tutorial,
Yes.
the properties for the T-beam and for the slab reinforcement were different. But when we were modeling it in SAP, so it is considering the same reinforcement throughout the flange section.
That you have to define separately. Proper. Can you explain what was the difference in T-beam and flange section in your question?
Sir, it was given bar dia 16 mm for the T section, and for the slab reinforcement, it was given 12 dia at the rate 150 center to center.
Okay. Bar dia 16 for flange section. That was main bar, right?
Yes, sir, main bar.
And for this one web section.
Uh, Sir, it was 16 dia only for the
Six.
web section as well at the bottom.
Okay, that was main reinforcement.
Yes, sir.
And what about the stirrups?
Sir, four-legged 8 dia.
Okay.
It was four legs along the width and two along the height.
Yeah, so that I understood. Now, question actually I am not clear. What question you asked? What was the doubt?
Sir, I am saying that this reinforcement that is provided in the slab section, it was
Huh?
given as 12 dia. So when I am changing that, the whole flange plus slab section reinforcement is providing same. So
Okay.
how can we provide it separately?
It means once you are, for example, I am changing this one, so all together is getting changed. That you mean to say?
Yeah, along the slab section. Yeah, whole is getting changed.
Okay. No, it should not happen. Now, see, suppose I click on this top left corner, this one. Okay, and I change anything here. Instead of 20D, let me pick 28 for example, and until you click on this
Hmm.
checkbox here, it will not get changed automatically for other corner bars. Okay, let me check this one. Now you can see only this one changed, right? Remaining everything remains same. But what happens if you
Yes, sir. In simple questions, it was like this only.
hmm. Okay, so you mean to say again
But
if I
with the
take.
T section, I was having this problem.
Okay, that I think it is better to take one new section only. So I'll go back and I'll create one new section. Let me take any random shape, okay? So I'll not take any particular dimension, I'll just make a shape of this. So now I want to add reinforcement. Okay, so I did this. Now I want to change, for example, this bar, and I want to make it to 20. I think it's working fine, right? You can see I am changing the diameter of one of the bar, but the other bars not changing. Only that bar which I am trying to change is getting changed. Hello, it was Ashima, right? The question asked
Yes,
by.
sir.
So you can see here, right?
Yes, sir.
Okay, that was your doubt.
Um, Sir, I'll get it. I'll get the file checked by you once, it will be more clear to me by that.
Sure, sure. So what I have explained,
Yes, sir.
that was
Thank
the
you.
that was the problem you had, or it was something different than that.
No, sir. It was something else. I'll get it checked by you once. No, so that will be more clarified.
Sure, sure. We can discuss. You can come to me. We can discuss this.
Yes, thank you, sir.
Okay. Okay. So anything else other than this by anyone? Aniket, you were asking some doubt. Is it clarified or you still have doubt? And Shiv Kumar
Yes, sir.
also.
Yes,
Yeah.
clear, sir.
Is
Clear.
it?
Thank you.
It's clear, right?
Yes, sir.
Okay.
So we can't provide ties in ETABS, na? We have to use SAP only.
Yes, yes. In ETAB you cannot provide
Yes.
that. Software will consider it automatically, but you cannot control that. Okay, so if you do not have any more doubt, we can continue with our building model, I think. And in the last discussion we have seen how to design the frame structure, how to check the reinforcement of beams and columns, and in this discussion our slab modeling is not considered because we didn't model the slab, so we will not be able to see the reinforcement. That we'll see some other time when we consider model and the slab model also. Okay, now see in this part, once you complete the design and you want to check the performance of the structure under the seismic load or under any lateral load. Okay, there are two procedure. One is to run the nonlinear static analysis and one is to run the nonlinear dynamic analysis. Okay, nonlinear static means it is also known as the pushover analysis. Okay, so before discussing the pushover analysis, I would like to know whether it is already discussed in the class or you have some idea regarding the pushover analysis or not. Anything, whether you know at least something about the pushover analysis or you know something in details. I just want to know whether you have any idea or not. Okay, so I guess you do not have any idea. Let me have a small discussion on that. Okay, so let us take this example structure, and what I want to do is I want to apply lateral force here. Okay, with a particular pattern. The pattern can be anything, which we'll discuss later on. So in this case my load pattern is this one. As you can see, this is the load pattern, little bit parabolic. Okay, so now say I have applied some kind of lateral loads on a building. Here it is parabolic load pattern. Okay, and load is acting at the floor level, each of the floor level. Okay, and I have to check now the performance of this building in terms of the roof displacement. Okay, so this is the roof level, and because of the application of this force, how much displacement is happening in each of the floor. Okay, that I will be checking, and as a reference we always consider the displacement at the roof level. Okay, so if you consider this as delta, the displacement of the roof, delta r, let's say. Okay, and the base shear. As you can see, I am applying the lateral load on this building. So what will happen at the base of the structure, it will provide some resistance because of the foundation, right? So that resistance, let's say this is VR or VB. This is same as the base shear. Okay, so what I will be doing, I'll record delta R versus VR. Now say I am controlling the displacement. It means at the top I am providing some displacement. This force, it can be either in terms of load or in terms of displacement. Okay, for example, you can apply 10 kilonewton load here, or you can say you can apply 1 mm displacement here. Both way it is possible. Okay, so when we apply the displacement, it is called as displacement controlled. When we apply the load, it is called as force controlled. Okay, usually we go for displacement control, so I'll discuss that one. Now say I am applying the displacement of 1 mm at the first step. Okay, I am applying displacement of 1 mm, and because of this displacement, the structure will provide some resistance, and means some force will also be created, and because of this force, resistance will be created at the base. So this resistance, now say because of 1 mm I am getting 10 kilonewton resistance here. VR is equal to 10 kilonewton, let's say. So this I'll plot in this graph. I'll have displacement of 1 mm, and in the force axis I'll have 10 kilonewton, so I'll get this point. Next, in the second step, I'll increase my displacement by next increment. Let's say I am increasing the displacement linearly, so next step will be 2 mm linear increment. Okay, so now this becomes 2 mm instead of 1 mm, it is becoming 2 mm now. And this resistance, let's say now it is becoming 25 kilonewton. Okay, so you'll have 2 mm ordinate here, and you have 25 kilonewton ordinate here, and you are getting this point. Okay, so like this you'll keep on increasing this displacement 3 mm, 4 mm, 5 mm until the structure is failing. Okay, and for each of this incremental step you'll record the force or resistance, how much is generated here. Okay, and finally you will get some curve like this. Initially it will go linearly until the structure yields. After yielding, the slope will reduce. Okay, so you'll get something like this. Okay, so this is the curve of base shear versus roof displacement. Okay, or force versus displacement, some kind of parameters will be there, and it can be movement versus rotation also. Instead of displacement, you can record rotation also. Here instead of force you can record movement also. So all are possible. So when you apply the lateral force and you record the performance in terms of displacement, force, or movement rotation, like this curve is called as the pushover curve. Okay, and the procedure to run this analysis is called pushover analysis. So this is the basic about the pushover analysis, and I'd like to ask here, if you have any doubt, at least you should understand the basic. Okay, once you understand this one, we'll go to the model and we'll see how can we run this in ETABS. Okay, so if you have any doubt with this basic understanding, you can let me know. Okay, so if not, we'll go to our ETABS model. Before running the pushover analysis, you should run the gravity analysis and design. Okay, So because if you do not do the design part, then you will not have any reinforcement for your members, and without reinforcement it will not be able to provide any resistance or any parameters what you need in pushover analysis. Okay, so gravity analysis you should do, and the design also. Now we'll analyze our structure and we'll do the design. After that we'll move to the pushover part. Before running, let me create the pushover load case. You have to go to load case, then first you have to create one nonlinear gravity load case that I'll discuss later on. Let us name it gravity, and here instead of linear static you have to select nonlinear static. Mass source you can select whichever mass source you have defined, and it will start from zero condition. Okay, and here all the gravity load will come. Load pattern that, then load pattern floor finish, then load pattern live floor, then you have load pattern slab loads, then you have load pattern wall loads, then you have load pattern live roof. So this you can ignore also, live roof you can ignore, so I will ignore this. And live floor you can give 50%. This is similar to the seismic weight. Okay, so you can give 50, and remaining everything we have given full. Then next step you have to create pushover load case for each of the direction. First I will create pushover for x direction, push over x, it will be nonlinear static, and
ये रिकॉर्ड हो रहा है ना तो?
yes, yes. Here I cannot see, but it is recording. Actually I have started that recording. Don't worry, if you have doubt we can discuss anytime, many times, how many times you want we can discuss. Okay, so pushover analysis you can run in different way. See, as you can see, you can apply the load also if you have any particular load to apply, or you can apply in terms of acceleration, or you can apply in terms of modal formation. Okay, so here we'll apply in terms of mode shapes. It means the load pattern what you can see, this one will take from the mode shape. For example, your first mode shape is like this. Suppose this is your structure, and this is the mode shape. Okay, so this load will be applying in terms of this shape if you chose the mode shape. Okay, so that was the meaning. Usually we go for this mode shape only because our structure is considered to be assumed to be fundamentally means fundamental period dominated, and we consider the mode shape of the fundamental period. But suppose you are running the pushover analysis for one structure where fundamental mode is not dominating, there are multiple period contribution, then you can run, but it will not be okay to consider that as a reliable analysis, you can say. Okay, so that you have to remember when you can apply this concept of fundamental mode. This mode shape, and this is mode 1, and see here mode 1 you can decide after running the modal analysis only. At the moment I am not sure which is the mode 1 for this x direction. Let me check. First I will run a rough analysis to check the modes. Let us ignore these two cases. Sorry. Okay, analysis is done. Now I'll check my mode shapes. This mode 1 and apply. Here you can see both original structure and deformed structure. Can you let me know which mode is means in which direction this first mode? Is it in x direction or y direction? Ordinate you can see here. This is x and this is y. So can you now tell me which mode is this, x mode or y mode? This is the deformed shape, deformed structure, and this is the original structure. I think you'll more understand from the elevation view. So let me pick one elevation view. As you can see here, it is y, okay, and it is deformed in y direction. So should I consider this as y direction mode or x direction mode? Anyone who can tell? This is actually the mode means translational mode in y direction. It means the structure is vibrating in y direction. Okay, so we can say the first mode is the mode of y direction, not of x direction. Okay, next move to the mode 2. Here you can see which mode is this. Here it is written mode 1. Okay, so mode 1 is the fundamental mode of y direction. Next see the mode 2. Now you see mode 2, but in y direction you cannot see any changes. It means this mode is not in this direction. So let me change to x direction. Now you can see here deform shape. Okay, it means the second mode is the fundamental mode of x direction. Okay, now remember these two things, and now we'll go to our load case. Push over x, modify, and here this is the mode, and here I have to give the fundamental mode number. So here which number should I pick, 1 or 2? I want to define the pushover case considering the fundamental mode of the respective direction. So here I am defining the pushover case for x direction. I have to pick the fundamental mode of x direction, and as I have shown you now, two modes, one is in x direction, one is in y direction. So which was in x and which was in y? Second mode was in x. Okay, I think you still have confusion, so let me go back to that again. See the direction you can see here, this is x. Okay, and I think you can also check from this display structure output modal information. You can check here mode participation, and okay, let us see what can we check here. See, this is the first mode, and contribution you can see in y. Okay, it means it is confirmed that this mode is the mode of y direction. Then you can see second mode. Okay, contribution is in x, but there is no contribution in y. Okay, so this is the first mode of x direction, and like this you have to identify which mode to consider for defining the pushover load case. Okay, we are not considering the remaining modes. only the fundamental mode of x and y direction. Okay, so we have identified this is the fundamental mode of y direction and this is the fundamental mode of x direction. Like this you have to define. So our fundamental mode of x direction was 2 and scale factor will be 1, and we'll start from the gravity. It means before running the pushover analysis, it will consider the output from the gravity analysis. Okay, so whatever the load patterns we have defined under this gravity, it will consider the output after considering those load effect. Okay, for example, because of this gravity load structure deformed by 2 mm, let's say. So when you are running the pushover analysis, the structure will not start from the zero condition, it will start from 2 mm deformation which occurred under the gravity load. Okay, so this is the meaning of this we are considering at the end of this analysis for pushover. Okay, then geometric nonlinearity p delta we have defined. Then load application, let's see, that is displacement controlled as we have discussed, and here you can decide how much displacement you want to push your structure. Now let's say I want to push till 500 mm. Okay, so there is no limit, this you can set. So roughly I have given this up to 500 mm I want to push, and you will be controlling the displacement in x direction. So it is u1 is in x direction, u2 is in y direction, u3 is in z direction, and r1 r2 r3 are the rotation. So I am controlling the displacement. Story 10 means roof level, and this is at joint 1. So if you go to the plan view and select the joint, there are a number of joints at which joint you want to consider your displacement. So here you can enter that one. So I want to consider the joint 1. Okay, then okay, then results saved, multiple states. It means when you are running the analysis, how many steps you want to consider, whether you want to consider the 5 steps or 10 steps or 100 steps or 1000 steps. So this you can decide here. So I want to consider minimum 100 and maximum 1000. Okay, so software will understand in between this many steps it can take anything. Okay, then these are the numerical analysis parameters. If you have knowledge you can change this, otherwise keep it as default. So this is about the pushover in x direction load case. Similarly we can copy this for y direction also. So I'll change the name here to y, nonlinear static. Again it starts from gravity, and now mode will be 1 because we have seen the fundamental mode for y direction is 1, and the remaining thing already we have done. Okay, so analysis is already done, we have done the analysis. Now what we'll do, we'll go to the design. These things already checked in last class. So let us quickly run the design. Okay, so after running the design you can check if you have any error or any failure. If you have, you can check. first go by this, identify all failure, and you can see here beam column capacity ratio problem. So what you can do, you can increase the size of the column so that reinforcement can be reduced or capacity can be increased, or you can increase the reinforcement so that capacity can be increased. So these things you can control. But at the top story you can ignore that. When you check the beam column capacity ratio, usually we ignore the top story, so I'll not consider this as a problem. Okay, I'll ignore this, but remaining story you can see there is no problem, everything's fine. Then let us also check rebar percentage. So it is ranging between 1.5, 1.5, 1.3, and at the corner columns it is 0.8. So in the last class I told, if you are getting 0.8 throughout, it means it is considering the minimum uh, applicable reinforcement as defined in code. So your column is oversized, you can reduce the section for this. Okay, so I'll show this one also. What to do for that, go to define section properties, and you can edit all the corner columns. So this BE whatever I have defined, I think this is for corner columns. What I'll do, I'll change the size. Okay, so instead of 400, let me pick 350. This is for foundation, then story 1, story 2, story 3, story 4, story 5, like that. So these things are not by default. Okay, you will not get this. I have defined for my model, so that's why it is there. Initially when you do not define anything, you will not get these things that you have to do. Okay, go by the new property here. Here we'll edit, here we'll edit these names and everything, other parameters, then it will show in this. Okay,
हेलो
yes.
सर, आपने टॉप स्टोरी के लिए कॉलम टू बिम रेशो चेक क्यों नहीं किया? मतलब क्यों नहीं करते?
एक्चुअली टॉप स्टोरी में वो जितना मिनिमम प्रोवाइड करता है ना बीम कॉलम कैपेसिटी रेशियो, इसलिए अगर बीम कॉलम कैपेसिटी रेशियो कम, मतलब क्या है, ये फेल होने का चांस है। ठीक है,
हाँ,
अगर फेल होगा भी, फॉर एग्जांपल द स्ट्रक्चर इज फेलिंग, व्हाट इज गोइंग टू फेल, टॉप कॉलम और टॉप बीम, राइट? So it will not affect the
यस,
performance of the whole structure. But if
ओके,
suppose some intermediate story columns are failing, then it will affect the global structural performance, right? So that's why usually we
ओके,
ignore that top story one. It
ओके,
will have the local failure criteria, maybe one column or one beam will fail, so that we can easily repair, right? We can retrofit or we
यस,
can do the repairing, so that is no problem.
ओके,
Okay, so let us now run and see once again what changes we can get. Sorry, this is running pushover also. I have to cancel this. So analysis is done. Go to design. Okay, so actually I have changed the reinforcement details, sorry, section details for B. So as you can see, elevation view B. So that's why here it is changed little bit towards the bottom stories. You can see top stories still we need to change. Okay, if you want to optimize, but for the corner columns it is actually coming under A, as you can see. So I haven't changed this. So at least you have understood how can you do these changes. You can change the size of the section, and accordingly your reinforcement details will get updated here. As you can see here towards the bottom stories it is increased little bit. Now it is fair, I think 1.6%, 1.72%. This is fair enough. Okay, so like this you can optimize. Now leave it, will not change anymore, and when you are doing your model you can do like this, how I have done now. Okay, now before running the pushover analysis you have to apply the hinges. Okay, so again I would like to ask whether this term hinge is familiar to you or not. Let us consider one simple frame, portal frame. And I am applying lateral displacement or lateral force, whatever. So I'm applying the force. Okay, so this is going to deform. Let us consider this is the deformed shape. Okay, and if this topic assembly if it is going on in your ERD, I think you will be familiar with this. So that assembly part, is it currently going on in your ERD? Which topic is currently going on? Hello.
Design the purpose.
Design of okay, leave that, we'll discuss here. So when the load is applied, the structure is going to deform, and as you keep on increasing the load either in terms of force or in terms of displacement, so finally it is going to collapse, or finally it is going to fail. Now the whole structure is not going to fail. The failure will occur at a particular location, okay, where the moment is maximum, that there it will be damaging, or it will be failing at that point. So in this structure, if you see, the maximum movement will be here. If you consider this column, the maximum movement will be created here and here. Similarly, if you consider this beam, again maximum movement is going to be created here and here. And if you consider this column, again here and here. Okay, so going by this concept, we can say there is a chance of failure at this point somewhere in this range. Similarly, there is a chance of failure at this point somewhere here. So let's say here, and similarly at this point also somewhere, depending on where the movement is maximum, and similarly here. Then similarly here, and similarly here. So what we do, we assume that instead of considering this this whole length, the failure will be concentrated at a particular point. Okay, so this will simplify our computational procedure, and it will also reduce the time required for running the analysis. Okay, so instead of doing that, you can also you can consider the whole structure. You can consider the failure can occur at each and every part of the structure. It means the whole length you can consider for failure, and you have to give the nonlinear property in the whole length. If you do that, if you define the nonlinear property for the whole length of a member, then it will hugely complicate your analysis, and it will take lot of time. Okay, so to simplify that one, we apply our fundamental, and we roughly predict where the failure can occur. There only we provide the nonlinear definition, so that we can reduce our analysis time, and also the software can analyze at least the structure. Okay, because the unnecessarily, if we complicate the structure, software sometimes will not be able to run the analysis. It will not converge, so it will show the error. So like this point where I have shown these dots, these points are called hinge point. Means there we are defining the hinge. It means here only we are assuming that the structure is going to fail. Okay, similarly for this beam we will define hinge here and here, and for this here and here. Okay, and this is called concentrated plasticity definition. Okay, it means we are assuming that the failure point is concentrated at a particular point, not in the whole member length. Okay, similarly there is one continuum plasticity, or fiber plasticity, I forgot the terms actually. Concentrated plasticity is the one where we define the failure point at a particular point, as you have seen here. So this is called lump plasticity or concentrated plasticity. Okay, LUMP, lump, or concentrated. Concentrated you know already. So lump or concentrated. Okay, this one. Now instead of this one, if I do like this, so these are the columns, and sorry, this is the beam. Okay, now instead of concentrating the failure, means expected failure at a particular point or particular region, I want to consider this whole length. Means I am assuming that the failure can occur at any point. Okay, so whole length should be considered for nonlinear modeling. So what I'll do, I'll provide my nonlinear property throughout the length of the member. Similarly for this also, I'll provide nonlinear property throughout the member length, and similarly for this also. So like this for this also, for this beam also. Okay, and this is called distributed plasticity. Sorry, I could recall this one. So this is distributed plasticity. Distributed plasticity. So your nonlinear definition is distributed throughout the length of the member, with the expectation that the structure can fail at any point, means at any particular point within the whole length of the member. Okay, so this is the difference between concentrated and distributed plasticity. Now see, why should we go for this distributed? This is because if you want to get more accurate result, if you see in this case we have concentrated a particular length here, we are assuming that beyond this length, this region, if you consider this and this, we are assuming that our structure, this length is completely safe, means there is no failure going to happen in this range. Okay, so we are overestimating the capacity of the member. Sometimes what happens, the structure may fail in this region as well, but we are not considering this. Okay, but if you consider this one, it will more accurately estimate the failure. Okay, for example, because of some load, if suppose failure is happening in this point also, this region also, so this can predict this one, because you have already given the nonlinear definition. Okay, so this is more accurate. Distributed plasticity concept is more accurate, but the problem is it is more complicated. It will take a lot of time, and sometimes the analysis will not be able to run also in the software. Okay, so to simplify this, we usually go for this one, and most of the cases, the whatever result we get by considering the lump plasticity is accurate enough. Okay, accurate enough means it is not more than this distributed plasticity, but still it is reliable. Okay, so considering the time and accuracy, we feel that this is enough and sufficient. Okay, this is the thing you have to know. And now let's see how to define the hinges. Hinges is nothing but the capacity of the structure in terms of load and deformation, again that will define for a particular member. Okay, again for example, if we are considering this column, let's say the property of this column is this column. Let's say this is 400 by 400 section, and you have reinforcement 2 bar at top and 2 bar at bottom. Now if you have these details, you can estimate the capacity of this section, right? As you have done in your ERD, you have one section, you have reinforcement details, and you can calculate MY and MU. Yield movement you can calculate, ultimate movement you can calculate, similarly yield curvature you can calculate, and ultimate curvature you can calculate. Okay, now if you have these details, if you know for a particular section, you can plot this. This is your phi y, sorry, this is your phi y, this is your phi u, and this is your my, and this is your mu. Okay, so what you can understand here, for a particular section you have particular capacity curve. This is called capacity curve. Okay, this is also similar to the pushover curve only, but in terms of a load deformation curve for a particular section, not for the whole structure. Okay, this is at the member level, and for a particular section this curve will be constant. It means 400 by 400 section with 4 reinforcement bar. Okay, so this curve will have a means fixed nature. Either you are providing at the top story, or you are providing at the bottom story, or you are providing at the intermediate story, the capacity is not going to change, capacity will remain same. The demand can change, how much force is coming to that member can be different, but the capacity of that member will be same always. Okay, so this capacity curve will feed here, will tell that this section has this much of capacity. Okay, so this is the hinge definition. We'll see how can we input this. So this is the thing you have to understand, the capacity of the structure we are going to feed to this hinge. Okay, so this is also called backbone curve. Similarly, here also will provide, then here also will provide, here also will provide. Wherever we are going to define the hinges, there will provide these details. Okay, the capacity of that section, either in terms of movement curvature, or load deformation, or rotation. That parameter can be anything, so we can define. Okay. Okay, so now if you understand this one, let us go back to our ETABS model and we'll see how can we define this. You can now unlock your model. See, there is one thing I told in the previous discussion. If you unlock your whatever output was, it will be going to erased, but the thing is it will be stored until you run your next analysis. Okay, now as you can see, I have unlocked the, you cannot see any readings here, or you cannot see any output here, but it is stored in the memory. It is still not erased, but if you run your next analysis, that memory will be erased. Okay, so this is important. If you want to run the pushover analysis, your design data should be saved. Okay, because the capacity what I have shown here, to determine this capacity you need the reinforcement details. Reinforcement details will come from the design. Now if your design data is erased, so you cannot get those capacity curve, right? So that's why your design details should be saved, and that's why I am repeating this. Until you run your next analysis, your design details is saved, so you do not have to worry about that. Now let us define our hinge. First I will define the hinges for all the beam sections. Select, go to select object type, and here you can select beams. I am selecting all the beams together. This is again I am assuming that I have the one type of hinge for all the beams, that's why I am selecting all the beams together. But if you suppose you want to define different types of beam for different members, then you have to particularly select those members only, then you have to define. But at the moment I am defining same hinges for all the beams, so I am selecting all together. I have selected, then go to assign frame hinges, and see here some auto hinges are there. Means software by default defines some hinges that we can go for, or else we can define our own hinges also, that I will show later on. Okay, now let us start with auto hinges, and see below the auto hinges you can see lot of other hinges that actually I have defined for my model, that's why it is showing here. Okay, so let me delete all this, so that you can get the glimpse how the software looks like for the first time. If you see these things, I'll delete. Now you can see there is nothing other than auto. Okay, so this auto hinge, and here you can define your distance at what point you want to consider your hinge. Now again come back to this. Let us say from this end at 5% of the total length I want to define. This is the 5% of total length. So this is the total length of member. The 5% of this total length I will consider this hinge. Similarly again here from this point, this is again 5%. So if I go from this point, it will become 95%. So what I can say, at a distance of 5% and 95% of the total length, my hinge will be located. Okay, so accordingly I can define here 5%, 0.05, and add. Now I am defining for beams and the backbone curves. This I'll discuss later on. Now for the time being, let us consider this ASC 4113. I'll show you what it means. Okay, now let us consider this from table in ASC 4130. Just give me 2 minutes. Okay, so this you have selected AC 4113 and select the hinge table for what, for concrete beams. Okay, so these are the type of the members for what you want to define your hinge, and this M3. So as you know, in case of beam we usually consider movement in third direction, M3. Okay, and this is the gravity load case what we have defined earlier. And here you see reinforcement ratio from current design. This means the design what we have done just now. Okay, so it will consider the reinforcement according to that design what we have run now. Okay, and here you see transverse reinforcement is conforming, means we are considering the ductile detailing. We are assuming that our structure is provided with the sufficient ductile detailing. Okay, if you do not want to consider the confinement effect or ductile detailing, then you can ignore this one. Okay, and this drop load after point E, this I will discuss when I will show you the code ASC 4113. Okay, so this is at a relative distance of 0.5. Similarly we have to define one more at a relative distance of 95, and the properties will be similar. Concrete beam gravity, okay, close. Now you can see what is changed in the model. As you can see, some black dots are visible, so these are the hinge basically in terms of load difference. अभी क्लास ले रहा
ओके अभी रुके थोड़ी देर रुके
15 मिनट 6 बजे तक
नो प्रॉब्लम कर लो आप
ठीक so this is the hinge definition for beam. Similarly you can go to select the columns, select object type, columns, select, then go to assign frame hinges, again auto, and 0.05. so this will remain same code. Here you will go to concrete column, and here you see you have different options. So the meaning of this PM2 M3 is PM interaction curve. Basically PM2 is in one direction and PM3 is in another direction, so it is basically PM2 M3 interaction. Okay, in case of column. And here again the gravity load case what we have defined, and flexure and shear we want to consider from current design, and drop load after point E. Okay. Similarly at 95%. So now you can see for each column there are again 2 hinges provided. Okay, now we have done with our hinge definition, and we can now run our pushover analysis. Before running, let me show you one of the hinge how it looks like. Actually go to your hinge, then show generated properties. You can see lot of the hinges are now visible. So these are the hinges which is defined for your model. Okay, you can go to one of the hinge. Let me pick one of the beam hinge. Okay, you can go to beam or column hinge. Let me first show modify hinge property, and you can see this is the backbone curve how it looks like. And if you could recall what I have explained here, this one, if you compare this with the one what just now you have seen, it looks like this. So this is similar to this part, first bilinear part. This much I have shown you here. Then beyond this is the failure. Means after this point, if you see, after this point if you keep on pushing, what will happen? It will fail. Suddenly the moment capacity will reduce. Okay, so that's why it is coming down. Then again it will have some residual strength. Beyond a particular point, if you keep on pushing, so the capacity will not become zero. At a particular level it will become constant. Okay, so this is the residual strength. So this is similar to this one what I have shown in terms of moment curvature curve, and this is what is given in code ASC 4113. So this is in positive direction and this is in negative direction. Okay, in ASC 41 code you will basically get these parameters for a particular section and reinforcement, how much this rotation at each of this horizontal axis is, this one rotation for a particular rotation, how much movement, or for a particular movement how much rotation, like this. So these details are given in ASC code. Okay, so that things we will see later on. Similarly you can check your other hinge parameters also, and let us now see one column hinge. So this is column hinge. Column hinge basically will get in terms of PM interaction. So this is the PM interaction. You can see you have P, you have M2, you have M3. This is at a particular angle, okay, or particular curve. Here you see how many curves here, then you have curve 2. So this is corresponding to a particular angle. Okay, and these angles you can see at what angle this PM interaction curve is plotted. So you have 0 degree angle, then 45 degree, 90 degree, 135, then 180, like this up to 360. Okay, so for a particular angle, this moment curvature, sorry, PM interaction curves are given. These things you can explore. Then okay, now let us run one pushover. These things I will not run again, this is already done. I'll run gravity and pushover X, run these two. Let us see what we get. This is the details of your analysis. See these things: saved step, total 1000 steps I have considered, the null steps I have considered 50, total steps, okay, iteration maximum 10 iteration, sorry, maximum 40 iterations we have considered. So these details you can modify in the numerical parameters details what I have shown. I'll show once again after this analysis. See the null step, what you can see here 50, and below that one reading you can see it is increasing. So once this reading is reaching this 50, this analysis will get stopped. Sometimes what happens, because of this problem, if your structure is complicated, here you can see my model is run up to 70%, 0.7 you can see, means 70% completed, but it is not going beyond that. Now if this limit is reaching this 50, that analysis will get stopped. So what you can do, you can increase this limit, null step. Similarly this also, total step you can see 1000 is maximum. If it is reaching this 1000, then analysis will get stopped. Okay, so this happens, these things you can modify. Let me show that how you can modify these details, and after that we'll see the results. See nonlinear parameters you can see here, then you can go to this option, and here you can control all these: maximum total steps how many you want to consider, maximum null step how many you want to consider, then maximum iterations 10, 40 how much you consider, and tolerance, this also you can consider how much tolerance you want. Okay, so these things you can edit here. This will get experience after you start this pushover analysis, and once you run few models, maybe 3-4 times if you do, you'll have a rough idea about that how much you have to keep for a model. Okay. Now let us check the result. Static pushover curve. So this is your curve. Okay, as you can see, initially it is linearly increasing, then here it is somewhere here in this range, it is the yield point, then this is the plastic region. Okay, and ultimate point, after that it is failing. So this is the pushover curve, and if you want to get the Excel file of this, you can get from here. Okay, go to this option, then select formatted, and you'll get one Excel like file, and you can click on this XLS, so it will give you the Excel sheet of this. Okay, so this is the Excel sheet you have. These things I think today I'll not be able to discuss, so these things we'll discuss in the next class. Only the pushover curve I'll discuss now. So here you see the displacement and the force. So the displacement is showing in the negative, that's why you'll get this curve in this negative direction. You can change this, multiply this negative readings by -1, so you'll get the positive, so that your car will be in the positive axis. Okay, so you can plot. This is the pushover curve. So in x direction you have the displacement, in y direction you have the base shear. Okay, displacement in terms of roof displacement, and base shear means the shear force at the base of the structure. Now whatever you want you can do with your pushover curve. Okay, similarly you can run the pushover analysis for y direction also, and these things we'll discuss in the next class. Okay, there is one more thing I need to discuss. Actually, last class we started discussion regarding the drift criteria check with respect to the code book, that I did not get time today. So next class kindly remind me this one, we'll discuss that. Okay, how to check the drift criteria for our structure. So we'll stop here, and you are expected to run the pushover analysis for both the directions. Okay, so you practice this one, and next class we'll discuss what is these things, where is that, what are the meanings of this, we'll discuss in the next class, and drift criteria also will check in the next class. Okay, so till then you can practice the pushover analysis in both the direction, and you can keep playing with this one hinges, beam and column hinges, and go to this hinge inside what are the parameters, and try to understand each and every parameter. Okay, so if you have any doubt, anyhow we are going to discuss again in details in the next class. And ASC 4113, you just try to download this. Sorry, I have this 4113, I'll share in the WhatsApp group. So you go to that, there is one chapter, I think chapter 9 or chapter 10. Okay, that I'll check and let you know. These details I'll share in the WhatsApp group, so you just read that code book. Okay,